And welcome to another Think of a Number. You there. Can you tell me how many 7s in 28?
4.
4! Absolutely correct. Slightly harder one here. How many 4s in 28?
7.
7? Oh, it's easier than I thought. Yes. Now, we're living in an age where everything is getting smaller. When you think about it, you've got microdots, silicone chips, and transistors. And we're packing more and more into a smaller and smaller space. So why not with numbers? Why does 28 always have to have 4 7s? It's a bit boring, really. Well, I've got a friend who's got a theory that it might not be actually working out that way. Ah, yes, that's absolutely right. You see, the reason is, today you go to school and you're taught that there are 4 7s in 28. But it could be that that's wrong, in which case you're remembering the right answer for the wrong reason. And the right answer could be completely different. I'll show you what I mean. Now, if we put 28 down there and divide by 7, well, we'll try it. 7 into 2 won't go. Right, 7 into 8 goes 1. Put the 1 up there, 7 down there. Take it away. 7 into 21 goes 3. So there are 7 13s in 28. You don't believe me. All right, I'll tell you what I'll do. We'll try it again to check out. And see what 7 times 13 equals. Are you ready? 7 3s are... And 1 7 is... 7. Add it together. 28. You still don't believe me. All right, I'll tell you what we'll do. What we'll do is write 13 down 7 times. Can you count with me? 1, 2, 3, 4, 5, 6. Is that right? 6, yes. 7. And if we add that up, add with me, it's 3, 6, 9, 12, 15, 18, 21, 2, 3, 4, 5, 6, 7, 28. You see, it absolutely proves that we've been doing our sums wrong, and you can get a lot more into a lot more numbers if you know how to pack them in. Thank you. Is it gone? Well, this program isn't about doing sums wrong, but it is about packing things in, getting as much in under pressure as we possibly can. So we'll start straight away. Can I have my costume, please? Thanks very much. I'll start with a coat. I'm going to be a bit warm in here, but that doesn't matter because I'll be talking a lot of hot air later on. Can you do that up? I'll also be looking at some very cold facts. I'm wearing protective clothing because I need it, but I should advise people in the audience to wear protective clothing, because I promise you, before the end of the programme, some of them are going to get blown up. I can have big goggles. Thanks very much, lads. Thanks. So we're all set. On we go intrepidly for a breath of fresh air.
Now, what I've done is breathe some of this stuff in here, and it makes me talk much quicker because I'm very high-pitched, so I can get a lot more into the programme by talking very fast. You see, all the programme will condense... I'm going back to normal now. It's going back to normal, and I'm normal. What I've been breathing there is oxygen and helium mixed, and this is the mixture that divers use at the bottom of the sea, because the pressure is very great, so they need a pressure in their lungs to equalise the pressure of the water. So they breathe oxygen under pressure and helium to fill in the gap. Now, the only effect helium has is it makes you talk squeakily, and it also feels rather cold. But nearly all gases are much colder than air. And the colder a gas becomes, well, if it gets cold enough, it turns to a liquid, just as steam turns to water when it cools down. However, gases need to get to very low temperatures to turn to liquids. And when they do, they take up a space about 1/600th of the volume they started out at as a gas. So in liquid form, gases are easy to transport. So to that end, a whole science of low temperatures has been built up, the science of cryogenics. This is liquid nitrogen. Now, liquid nitrogen freezes
at minus 210 degrees centigrade. But it boils at minus 193 degrees centigrade, and it's at about that temperature now. Now, you can't measure that temperature with a mercury thermometer, because this is what happens to mercury when you put it in liquid nitrogen. It's absolutely solid. And I've got a 6-inch nail here. And it's almost through the block. Absolutely solid mercury. Now, if we put that in warm water, it boils like mad. And you can hear it crackling. And slowly, the mercury comes off in little drops and becomes its runny old self again. I'll leave that there. Now, this liquid nitrogen, if I put my finger in, it would freeze absolutely solid, and it wouldn't thaw out till next Thursday. However, if we dropped meat in there, or vegetables, or even flowers, they would freeze. And in no time at all, be absolutely brittle. Just like cornflakes. However, if we let it get back to normal temperature, the flour would apparently be none the worse for wear. So if we can preserve things by putting them in liquid nitrogen and freezing them, could we do that with people? Well, it's been found that they can freeze sperm and eggs, and some insects and small mammals have been frozen and then brought back to normal temperatures and found to be none the worse for wear. Now, if you could do that with people, you could conquer space, because the only way to get to the stars is to travel hundreds or perhaps thousands of years through space. So you could put somebody in suspended animation and warm them up when they get to the other end. But to get us through space, we need some more liquid gases. We need liquid oxygen, and we need liquid hydrogen. This is a model of Saturn V, the rocket that was built to put man on the moon. It's 373 feet tall, but the top 80 feet is the actual space module itself. And the rocket is in 3 stages, 1, 2, and 3. Now, the whole weight of this is about 280 tons, but the weight at blastoff is 2,700 tons, because at blastoff, 90% of the weight is taken up with fuel. 12 million gallons of liquid hydrogen, liquid oxygen, and kerosene. The fuel is stored in refrigerated tanks in the body of the rocket. And they're so well insulated that if you left an ice block inside one of the tanks, it would take 8 years for the outside air to get in and melt it. Now, the power is achieved by mixing the liquid hydrogen or the kerosene with the liquid oxygen and burning it. And immediately it turns back into gas, multiplying in volume 600 times and pushing the gas out at the bottom. This forces the rocket up into the air until it accelerates to 25,000 miles an hour. And at that speed, it overcomes the gravitational pull of the Earth and sails out into space, propelled solely by the pressure of hot, expanding gas. As well as liquid gases, there are some liquids that themselves contain gas. This is lemonade. And lemonade contains carbon dioxide, which has been forced in under pressure. Cheers. I'm a secret lemonade drinker. And you've all got lemonade. in the audience, haven't you? So take the tops off the lemonade. Don't drink it yet. Or perhaps just a little bit out of the top, if you like. You've all got packets. Open the packet, take the top off, and you should find peanuts. When you've got a peanut, drop it in your lemonade and see what happens. It sinks and then floats. Okay, well, I've got a glass here. Put that on there. There's yours. Now, if you drop a nut in here, what happens is it sinks and then comes to the top. And as it sinks, it gathers bubbles. The carbon dioxide forms bubbles and buoys it up like a life jacket and brings it to the top. So have a go. See if that works. Yeah? Yeah. Great. Okay. I'll have that one back. And could I have 4 helpers, please? You 4 there. Could you come round here? That's it. Leave your things there. Now, we've got 4 more bottles of lemonade. If you open the bottles, just take the top off. And leave them there. And you've each got a bowl of something. This is salt. That's talcum powder. That's flour. And that's sugar. So you've got one each. Get a spoonful of your substance. Hold it at the top of the bottle. And when I say go, pop it in. Go. Look at the end two. Have really bubbled up because every single grain acts as a catalyst and brings out the gas. But the middle two haven't passed their physical. So let's try stirring them up. You do it. That's all it needs. Isn't that amazing? And it brings the gas out of the liquid. Like mad. Okay, thanks very much. There you are. You're all physicists. Huh? Or physiologists. So that brings the gas out of the substances. Now, gases are used in many other ways. Aerosols, for instance, have got gas which is released at the press of a button. That's soap. But we use gas in many other everyday things, like balloons. Oh! Now, although balloons are everyday things and great fun, there are lots of balloons that are very important, like weather balloons, and lots of other things that inflate with compressed air. Things like, oh my God, more balloons. Or one of these. Can you grab the other end, someone? Can you come and grab the other end, please? And pull it over here. That's it. About there. Now, do you know what this is? Well, it's a, say that again. Well, it might be. Hang on. It is, and the thing with the life raft is you must never pull this. Because if you do, it inflates very quickly. People have been known to survive for 112 days in the Pacific in one of these. So they're absolutely vital. It's also very rigid. You can stand all the weather. And it's very light. Can a few of you give me a hand to move it over there? There we are. It's as light as air, isn't it? Oh, thanks very much. And there's the cover. Those balloons. Because I've got something else over here to show you. When you walk about in the open air, you're carrying on your head a column of air, 5,000 miles high, weighing about a ton. At the top, there's the exosphere, which goes from about 5,000 miles down to 450 miles. Next comes the ionosphere, and that's where meteorites burn up, so they hardly ever reach the surface of the Earth. Then comes the stratosphere, which contains ozone, and the ozone protects us from harmful radiation. Lastly, the final belt is the troposphere, which is the very bottom belt. It only goes up to about 7 to 10 miles deep, but that small band contains 80% of the mass of the atmosphere. It also supports all living things, and it contains 17 million tons of water. And that water together with the varying pressures in the atmosphere, create our weather. The most violent of all kinds of weather is the hurricane. A hurricane starts at sea with hot air rising in a column and mushrooming out. And then, as the Earth rotates, it gives it a twist, just like your bathwater's given a twist and it spirals down the plug. Then you've got a hurricane. The outer edge travelling at about 200 miles an hour, but the centre absolutely still. Now, in recent times, we've been able to put satellites in the upper atmosphere so that we can predict our weather very accurately and take precautions against hurricanes, which is just as well, because it's doubtful that man will ever tame the mighty hurricane. Oh, it's got me hat. And there goes me hat. Right. I feel all windswept now. Have you all got pieces of wood in this part of the audience with a hole in? I want you to blow through the hole, holding it down, and the piece of paper I want you to hold underneath, right up close, touching, and hold it on the flat of your hand, a piece of paper. Blow hard, and when you're blowing hard, take your hand away. Anybody done it? You're not blowing hard enough, really hard. There's somebody done it at the back there. That was very good. What happens is, as you blow, the air fans out across the card, and moving air has got less pressure. Underneath, the air's absolutely still, and the high pressure holds up the card. And it's held on a cushion of air. And that's just how... Well, hang on a second. Hold that. You two, can you come out with me? Leave those there. You come first. Can you think of a number between 1 and 10?
9.
9. Righto. I want you to... this is a door. Doesn't look much like a door. I want you to count from 9 to 0. Ready? Go. 9,
8, 7, 6, 5, 4, 3, 2, 1, 0.
Right hand down a bit. It's a hover chair. Hang on. And it's the chair that's making those noises, not me. Right? What it is a chair with 4 pads. And I'll show you the pads. Perhaps we can tilt it. Up. I'll swing it round a bit. And there they are. 4 rubber pads. Can you turn the air on? Just slowly. Nice and slowly. More. And you can see the air flowing out. There it is. Okay, turn it off again. Now, that force is only about the same force as a vacuum cleaner, a normal household vacuum cleaner. In fact, Christopher Cockrell, who designed the very first hovercraft, used a vacuum cleaner in reverse for his first experiments. Would you like a go? Yeah. Sit on. And it's completely frictionless. You just get a bit of vibration onto the pads. Would anybody else over here like a go? You on the end? All right. Can you come and help, the two of you? I want you to bend down and guide this end. No, you stay there in your seat. Right? And guide that end. Because out they come. You didn't expect that, did you? The whole section of audience, and you need absolutely no pressure to move them. Other way! And back you go. Coming into dock. Don't worry about the balloons, they'll go. Thanks ever so much. Give them a round of applause. So there we are. We've seen that just air pressure can lift 1 person, or 9 people. And with the biggest hovercrafts, air pressure can lift 400 people and 50 cars. And when you think about it, it's air pressure that holds up every aircraft flying around the world. And the gases in the air also support not just aircraft, but support every living thing. Oxygen for humans and animals, and carbon dioxide and nitrogen for plants. So you could say the air is a very good friend, because the definition of a good friend is someone who'll support you, especially under pressure. We've got a trick here. Would you help? Would you like to help? 10 matches in each pile. I'm going to turn my back. I'd like you to think of a number and take that number away from each pile, okay? So if you think of 3, you take 3 from each pile. Have you done that? Yes? Righto. Now, from pile A, take 3 more and put them on pile B. You can scrap the rest of pile A now. From pile C, take 3 and put them on pile B. Now I want you to count the number of matches that are left in pile C. And take that number away from pile B. It sounds like a Jimmy Young recipe, isn't it? Okay, have you done all that? Now, I've got a seesaw here, if I can find it in my hand, which is very delicate. I want you to take some of the matches in pile B and put them in my hand. Any number, it's your choice. Okay? And the rest of them, I want you to put on the other end of the seesaw from the end I'm holding. And that's incredible, because I can tell with the variance in pressure that there are 6 matches on the other end. It worked? Yeah. 6. There you are. Well, if you'd like to know how that trick is done, it'd be my pleasure to tell you. But you'll have to write to me first. Johnny Ball, think of a number, BBC Television, London, W1A, 1AA. But please include a stamped address envelope. But time's beaten us. It's the end of another Think of a Number. And the more programs we do, I find the quicker they seem to go. And we get less and less in. So, perhaps one day, somebody will be able to perfect a system whereby we can squeeze a lot of things into just a fraction of the time. We take, that's it, slightly. Because if he changes down, bring one up. Would you like a go? You can scrap the rest till next week. Bye-bye.